So, good morning and welcome to lecture 2 of module 3. So, as we are discussing in the last class that this is a 3 lecture module, the triple lecture stuff on 2-level Boolean synthesis. So, we started in the last lecture with what is a Boolean synthesis. So, in Boolean synthesis we consider the output of the high level synthesis tool, or in other words we take some Boolean functions and try to represent them using minimum number of gates, minimum number of logic gates. In other words, you want to have a simplified representation of Boolean functions. Here simplicity means the number of literals should be minimum and the number of terms should be minimum, so that the representation of the Boolean functions can be done by the minimum number of gates. Then what we have seen, a very good way of doing it is that if we can represent the functions by prime implicants. So, what is a prime implicant? Already we have seen that this is the definition of prime implicant, and then we have seen that if you take only the prime implicants of a function, so we are actually going toward the minimality, because the prime implicant is such that which is not covered in any other implicant of the function. So, that means prime implicant will have at least some min terms, which is means that there is no other term, or you can say in which all the min terms which is in a prime implicant are a subset of that. That means if there is a term like, say, you can say x, y, z. So, if we think that x, y, z is a prime implicant kind of a stuff, so there will be no other term in that for representing the function such that where the whole stuff where x, y, z totally is embedded in that. Like for example, I mean this is not a prime implicant if you have a function like which says that some z plus say if f is equal to say a plus w x y z. So, if you think there is a function like this, you just remove this. So, x y z, if you think like this, so in that case you w x y z, this will not be a prime implicant. This cannot be a prime implicant because it is totally embedded in this one. So, what does it mean? That if you include this, automatically this stuff gets covered, and if you assume that it is a prime implicant for this function, in this case it is. Also, A is a prime implicant in this case. So, if that is what is the goal idea, that if you include this term, so it will actually have 4 literals 1, 2, 3, 4. But if you are implementing, if you are including a prime implicant, in this case x, y, z is, and this is not, because w, x, y, z is totally inside x, y, z. So, in this case here you have 3 implicants, so you require a 3 input AND gate, and in this case you require a 4 input AND gate. So, the basic logic was that if we are trying to take such terms whose the number of literals are small, less in number, as well as the number of terms are also small in number, less in number. So, we are going towards that. So, the first goal was, if we are given a function, we are trying to find out the number of prime implicants for this. That we want to incorporate the prime implicants in the implementation of the function, because prime implicants are such so that they are not totally inside any other implicant. So, that is why obviously the number of terms or number of literals will tend to be more, and then we will see how can we include some of the essential prime implicants or the prime implicants which will cover the whole function. That we will see slowly. So, last class we discussed one method which is called the tabular method, or also they call the Queen's method. In this case, this was one way of generating the prime implicants of a function. But this method was very simple, because we have to just divide out the all number of what you can say, we represent a function in the canonical form, and then we separate with no complemented terms, then 1 complemented terms, then 2 complemented terms, and so forth. And then we try to find out the consensus between terms of one row or the other. So, which you have already seen. That is a very simple procedure. But if you observe, this was our basic idea, if you remember. So, we had a table like this. So, this one is having only 1 primes, this one is having 2 primes, this is having 3 primes, there can also be a row having no primes. Then we have consensus in between these 2, and then between these 2 in terms of this set, and then finally we generate the next set of terms, and then again we have consensus between these 2, and finally we generate this one. So, this was the procedure we have already seen. Now, the main problem is that the good thing about it is a very simple procedure. Just you have to see about consensus between terms of some alternate, near about rows, adjacent rows. But the thing is that the procedure is exponential in nature, because if first you have to represent this stuff in canonical form. So, if it is a canonical form, in the worst case the number of terms in this can be order of 2 to the power n if the n is the number of inputs, because you see it is a 3 variable function. So, the number of terms can be in the worst case can be 8. So, in this case it can blow up in exponential nature in this length. So, that was the main difficulty. So, in today's class we will see another scheme of doing the same thing, but here we will not take a canonical form, or here we will not blow up the function and then we bring it down. So, if you look at the Queen's method or the tabular method, what we have done, we have taken a function and then we have made it in a canonical form. Canonical form is you are opening up the function, and then you are trying to merge terms or which are having consensus, and finally we will land up in a situation where no more terms can have consensus, can be merged. So, we are going to have what is the prime set of prime implicants for the function. But the main thing was it was an exponential. expression, so we had a problem. So now to cater to this issue, so we will see we will see another procedure which is called the iterated consensus based stuff. So in this case what we will do, we will not expand the product terms of SOP form to mean terms, that is that we will not go for canonical expression or we will not blow it up. So how will you do? So what we will do, we will have the given function in SOP form as it is, we will not open it up. Then the consensus of terms of all pair of terms that are not contained in any other term is added to the equation. So what we will do in this case, we will keep the terms as is, we will not make in a canonical form, and then we will try to have pairwise, we will find out if they are having any consensus. If there is a consensus, we will take out that term and we will find out that all the terms which are directly included in some other term will be eliminated from the expression. That is what, in other words, we will take all pairwise terms and we will try to find out a new term which is having a consensus. Now we will add that term, new term, to the equation or expression, and then we will find out that if there is any term which is totally embedded in any other term, and if it is there, we will eliminate those and then we will again redo it. Okay. Then the new terms are compared with the existing terms and among themselves to see any more new terms are generated. That is, first we take all pairwise terms and then we find out a new consensus term, keep it aside, and then we check whether any term is totally embedded in between in any of the terms, including the new one generated, and we eliminate all the terms which are already included in some other term, and then we again go for iterated consensus with the new term that is added into picture, and then again we repeat the procedures. Okay, again all the terms that are contained in some other terms are removed, that we do, and if no more terms can be generated, then we actually stop because all the prime implicants has been generated. So that is the basic flow. The basic flow is very simple. You take pairwise stuff, pairwise terms, do not open it up, take a SOP formula and SOP Boolean expression or whatever, and that expression given to you, and then what you do, you go for pairwise term consensus. Very important to note here that we are not going for a canonical expression form, we are just taking in these terms in this in whatever order they are, so that will be smaller if you remember. We will see with an example also. In the last class example, if you see the term expression was smaller, so you can see over this, if you just recall, we had this small expression. This was the expression, okay, and then in this case we have blown it up into this one because of the canonical expression. The size blew up and it can go to exponential bounds. Okay, so in the iterated consensus, what we will do, we will work with this. We will have in consensus between these two terms and again between these two terms and again between these two terms, and at every step we generate what you say some new terms, and at whenever we generate some new terms, we have to check whether all the terms which are already involved or totally incorporated in some of the terms has to be eliminated, and then we have to repeat it again and again. That is, we have to again go for iterated consensus with the new term added, and then again you have to find out if anything is included, and we keep on doing it till we find a case where no more new terms are generated. Then this procedure will give you what you call the set of prime implicants, okay. But you have to again prove it, because this procedure is what you do, you take in the tabular method the proof was very obvious by construction itself. So what you do, you open it up and then you try to find out that whether there can be any consensus, and you are trying it exhaustively. So it is obvious that you are going to get the prime implicants. Okay, but now you see the other way, here actually what you are not opening it up. So what we are doing, we are taking it the other way. So in this case we are not opening the terms, so we are keeping the terms as it is, and then we are going for the iterative consensus. So here we require some amount of thought that why it will give you the set of prime implicants. In the other phase, what happens in the previous thing, it is already we have opened it up fully, that all the individual terms have been broken into mean terms, and then we are trying to find out if each of the terms by checking pairwise terms that whether there can be any consensus, and then we do it. So there we actually do not require to do pairwise, because already we have separated out in terms of seeing no complement, single complement, two littles complement and so forth. So every like one complement with two complement, all terms are compared, no complement with single single literal complemented we compare, and we keep on doing it. So it means in other words, in a broad way saying that all the terms or in mean terms, we actually the expression is broken up into mean terms. Every term is compared among themselves to find out new terms and so forth. So obviously we get the prime implicants, but here actually the terms are not broken up. So we need some amount of proof that if we proceed this procedure we discussed, if we go about this procedure, so it will be done. So how is it? So you see, so this is just the definition. An SOP formula is a complete sum if it comprises all the prime implicants of the function it represents. So we say that if all the prime implicants are involved, it is a complete sum. Now we say SOP is a complete sum if and only if, that is a SOP formula has all the terms, all the prime implicants, if and only if no term includes any other term. That is very obvious. First term is by definition only, okay, because if any term is totally incorporated, included in any other term, then that has to be eliminated, and by definition of prime implicant, that is not a prime implicant. Like if there is a term called P and all the mean terms inside this one is included in another term called P prime, or say Q, does not put it prime because prime means complement. So if P is a term, Q is a term. So if all the mean terms in P are included in Q, then obviously P is not a prime implicant, Q is the one. So that is by definition. And second term is important, the consensus term of any two terms of the formula either does not exist or is contained in some other term of the formula. So what it is saying that if you take any, because we say that the complete sum has been generated, that is already, I mean, iterative, the whole iteration has been done, and finally we get an expression in terms of, that is, we say we take all the terms and finally no more new terms are generated, that is we have stopped. Then what happens? Then we say that is a complete sum has been generated. That means whenever we have stopped, therefore no two terms can be found whose consensus can be made. Okay, that does not exist, or if it exists also, then it is contained in some other formula. That is why we have not generated it. That is, if you take two terms, no, if some consensus can be formed, either it cannot be formed, then it is fine, but if it can be formed also, then it is already in some other term. That is why we have not written it down in the expression. So if this holds, there is a complete sum. So let us just see the basic philosophy of the proof. Suppose an SOP representing function is not a complete sum, we are going for the counter logic, because one prime implicant of the function does not appear in the SOP. That is the idea, because we are trying to generate by iterative consensus all the prime implicants. So let us see that, think that the procedure is wrong, and we generate all but one prime implicant by this procedure. So one prime implicant is not there. So therefore what happens? Therefore the remaining prime implicant must be covered by two other prime implicants of the SOP. Like some SOP is there, so you are representing in terms of P1, P2 dot 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 Pk. Okay, let us assume that since one prime implicant, say P, which is missing. Now what happens? So if it is missing, that means obviously some 2 or 3 or 4 prime implicants can have consensus to generate the prime implicant P, because this SOP is represented by this prime implicant excepting one. Okay, we are taking the assumption. The assumption is that by doing the procedure we generate P1, P2, P3, all are prime implicants. One prime implicant is however missing, but the procedure discussed in the last slide. This slide, okay, this one, this procedure. Okay, so now if this is the case, so one prime implicant is missing. So now as this all this P1 dot dot Pk represents the SOP, so obviously this P must be the P is a prime implicant. So obviously it cannot be directly totally included in either P1 dot P2 or Pk. But what it can happen? See, it has 3 mean terms. Say 2 of them are inside this, and say 1 can be in this. This is also possible. So for simplicity, let us assume that 2 prime implicants P1 and P2 actually can generate P. That means say P1 and P2. Let's say P have 3 prime same mean terms. So 2 of them are in P1 and the remaining one is in P2, because it cannot happen that all the 3 mean terms of P are included in either P1, P2 or Pk. Is not possible, because then P would not have been a mean term, prime implicant itself. By definition of a prime implicant, it cannot be in any one of the other prime implicants like P1, P2 dot dot Pk. That is the definition. So now what happens? It has 3. So 3 mean terms, 2 is in P1 and 3 is in 1. Okay, now obviously if we get the consensus of these two, we will get P. Okay, and P's will not be included totally in any one of them. So obviously P has to be in this one. So now that means what happens? So this our basic assumption was wrong. So if you go about this iterative consensus, always you will get all the prime terms of it. Okay, so this is a proof called counter logic. So we call it proof by contradiction. First we assume that the procedure was wrong, then we prove that it cannot be, because if you complete the procedure, the answer will always be correct. So what is the assumption here? If we have done all full algorithm, we have executed, and then we left one prime implicant called P. Now we say that the prime implicant generator are P1 to Pk. Now we assume that P has some k or l number of mean terms, so which are included in P1, P2 dot dot Pk. So for simplicity, we assume that they are in some of the implicant prime mean terms are in P1 and some of them are in P2, and somehow we have forgot to include P. So then what happens? Now you can say that the iteration was not yet complete. You take the consensus between P1 and P2, obviously we will generate P3, and then actually P3 will be also have to be included, because P3 is not in any one of them directly, not in P1, not in P2. Partially they are in P1 and partially in P2, not fully in any one of them. So but just by iterating the this algorithm one more, you will get P inside. So that it states that if you take about this example, then obviously you will get all the prime implicants. Okay, so this is called the iterative consensus. So what we do? We start from an arbitrary procedure, arbitrary SOP formula, as I already told you, and add the consensus terms in this was not contained in some other term. Already I told you, that is again repeated. Now the new terms are compared to the existing terms. Okay, and then you see that consensus can be, if some new terms are generated, then you add that and then again go for iterative consensus. And at any point of time, if you find out that and some term is already inside another term, you eliminate it. Okay. So, these steps actually already discussed generate a complete sum or the prime implicants. Okay. So, now we will take an example. Always this type of complicated definitions and all are better illustrated by example. Okay. So, we take this function. So, if you remember in the last class, this was the function x prime z prime x y z prime and this one. This is the same function in the last section or the last lecture. However, the don't care terms are here mean terms. So, if you remember this was our example in the last class, this one. So, this was our expression. In this case, this was the don't care terms. The last two terms were don't care terms. Now, actually we have eliminated the don't care and we make all those as mean terms. Okay. So, in this case, what our final this was one prime implicant if you remember, and this was another prime implicant if you remember, but then we eliminated this one because it contains only the don't care terms. But now there is no question of any don't care terms. So, our prime implicants are z prime and x y prime by the tabular method. Let us see if the same thing comes. Here there is nothing called don't care. So, just eliminate this. If you just eliminate these don't cares, then you will finally get x y prime and z prime by the tabular method. Okay. So, same expression we have used, but we have just eliminated out what is the don't care terms, correct? Okay. So, now don't terms are main terms. Okay. Now, what do you do? In this case, we do not expand it. So, if you remember in this table form, if you see, we actually expanded it. So, you see this one they have expanded it from here, actually they have this term they have expanded this one. Okay, this they have expanded it. So, in this iterative consensus we will not do it because expanding actually makes an exponential complexity. So, what do you do? Now, you see consensus of this and this. Okay, so, this is called x prime z prime and x y z prime. Okay. So, now you see in this case this z prime and z prime are matching. So, okay, only the x and x prime is there. So, directly you eliminate this x and x. So, what happens? So, you get y z prime. Okay. So, the first two terms z y z prime, which now this one is generated. Why? How? Because you see this is x prime z prime x y and z prime. Okay. So, there is one z prime is common and x prime is there. So, this get eliminated and we finally get y z prime from this one. Okay, this is what is generated from this one. Now, what you have to do? So, now you see this y z prime if you take. So, it obviously contains x y z prime. So, now you can eliminate this from the expression. Okay. So, now by iterative x and z prime we generate a terms this one which already contains x y z prime. By eliminating, you just eliminate this and add y z prime. So, what we have? X prime z prime remains. Okay, and then this is the new term we have added y z prime. Okay, and what do you do? So, y z prime we have incorporated. Okay, and this is what has been incorporated, and x y z prime this one x y z prime. So, this x y z prime this one is already embedded in the new term y z prime. So, this can be eliminated. So, finally, we have this as the equation. Okay. So, by this step first we compared these two guys x z prime and x y z prime, the first two terms, and generated this term. Okay. So, which contains also this one and this is added. So, first we add say y z prime, then if you can see in this case y z prime already this guy is included, x y z prime is already included in this one. So, this can be eliminated. Now, you can check that no other term will be totally included in this one, because obviously you can find out that this one is x y prime z. So, this guy is also not included here, and x prime z prime actually can be represented x prime y z prime and x prime y prime z prime. So, x prime y prime z prime will not be actually included in this one. So, these three terms will remain. Okay. So, only one term that is continuous was there, that is x y prime z prime is included. So, you can eliminate this. Now, what you can do is that, so this is our new expression. Okay. So, now the new expression x y z prime, this x y z prime, this is eliminated, this will remain, is x y prime z prime, is not included in this one. So, this is a new expression. So, in case this was actually x prime z prime plus x y z prime plus this stuff was there, Okay. So, now you can see that x y z prime is included in the last prompt, which is added. So, you remove this one and then finally you get this one, x prime z prime, x y prime z prime, this one, and this is new term added. Okay. Now, what you do? Now, again you take the consensus of x prime z prime and x y z prime. So, every alternate pairs you have to do. So, if you take this one, we will generate what? So, x prime z prime, x y z prime. So, in this case again you see that x and x prime is there, z prime is z prime and z prime is common. So, this x and x prime will be eliminated, which will generate the term y prime and z prime. Okay. So, now this y prime z prime you can add over here. So, in this case you can add y prime z prime. Now, you can see that x y prime z prime, that is the second stuff, is already included in the new term. So, you can eliminate it, which contains this one. By eliminating this one and adding this, we get the new function, this one. So, you can keep on doing this. So, all these steps are written over here. Okay, so, I am not going into details of all this. So, now you can find out that some of the terms like these two will not have any consensus, because you can see this is x prime and x and z prime and z. So, there is difference in two terms, sorry, difference in two literals with the complement, right, x and x prime, and in this case z and z prime. So, two places have different, I mean in terms of the complement. So, they do not have any consensus. If you keep on repeating it, you can see that 3, 4, 5 and 6. So, you get the final term, this one is x y prime plus z prime, which is similar to nothing but our this table form. If you see, this is what our is x y prime plus z prime. So, in the previous stuff we actually do not include this one, because this is only comprised of don't cares, but here we have to include, because now in this case actually nothing was a don't care. So, everything is actually you have considered as mean term. So, this is the case. So, finally, you have generated it. So, now in nutshell, so what do you understand? So, what do you get over here? So, we get two things. So, first thing is that in the case of iterative consensus, the complexity will remain low. So, how the complexity is remaining low? Because in this case we are not opening up the stuff, that is we are not opening it, this one, into a canonical form. This is what we started with. This is what we started with, and we have never opened it up into its canonical form, that we have not done. So, if you have not done, then we have started with this one and then tried with this two pair, generated a new term and then eliminated this, then we tried with this one and find out a new term and eliminated this. We will keep on doing it and we will finally get this expression, which is only the prime implicants. Now, in this case, as we have not blown it up, so the complexity is much lower than the tabular method, where it started off with a full exponential blow up. So, in this case, if you observe, it will be totally depending on how large you have written your SOP formula. So, generally SOP formulas are written in a small way, generally they are not very large, and even if they are large, it is somewhat okay. But if you take any SOP formula and go for a canonical representation, then obviously you have taken a full what you can call this what do you say, the full exponential complex you start off with, then actually you are starting off with a very big size of the problem and then trying to get the prime implicants. Here we are actually trying with a much smaller subset of the problem, and then we are not blowing it up, we are directly going to find out the prime implicants. So, in one case we start with a point A, then go high and then actually try to get the number of prime implicants. In this procedure we just try this one, you can say that tabular. So, here actually we are going to the prime implicants. So, in this case of iterative consensus, iterative stuff, we actually go this way, and in this case it is about this way. So, we go here, make it blow up to all the mean terms and then come down, and here actually we are going about this way. So, this is how the things are done. That is why it is actually order of lower complexity, fine. So, now what we have to do? Now, our job is that what we have to do? So, now we have found out all the prime implicants. Now, what do you have by definition, what you have seen by prime implicants? Prime implicants means you have say P1, P2, P3 dot. So, what is the basic philosophy? That note this P1 cannot be included totally here, similarly P2 cannot be totally included in P1, P3 and so forth. So, all these terms, none of these terms can be totally included in any other term, and it can be thrown away, that is not possible. But what can happen is that it may have it may have say 4 mean terms. Some 3 may be included here and 1 may be included, it may, or it may not be. It may happen that a prime implicant say P2 has say 7 mean terms. Out of that say 6 may be here, something like this you can think, and 1 is nowhere else. Then this becomes an essential prime implicant. This is essential because it has a mean term which is available nowhere. So, that is obviously you have to take this prime implicant into case while making the circuit. But other things like, say for example, if you find out that P1 has 4 prime implicants, 1 is in P2 and 3 is in P3. So, you can drop P1 and you can take P2 and P3, but the essential prime implicants are those which are having a mean term which is nowhere available. So, that is to be included, but some other prime implicants may be such that some of the mean terms of the prime implicant may be available in mean term prime implicant A and may be available in other in prime implicant B. So, what you can do, you can totally throw away this first prime implicant and take the rest of the 2. So, in the last lecture or last class, we discussed techniques to generate prime implicants given a Boolean equation. So, we have seen the tabular method, and today in the beginning of the class we have seen my iterative consensus method. Now, we have all this. Now, our main idea will be to select a subset of primes, okay, so that you can cover up the whole all the mean terms of the SOP, that is one thing, and then what you have to do, actually you have to cover, which is we will see the definition, we have to cover the function. So, why do you mean by covering the function? I think you know in your BTech undergraduate course that we write a function in terms of say 1, 3, 5, 7, these are the mean terms, say. Okay, so that means 1, 3, 5, 7 are the terms which are actually 1. So if 1 is applied, 3 is applied, 5 is applied or 7 is applied, you have to give the answer as 1, or they are the mean terms. So you have to include those prime implicants which actually cover 1, 3, 5 and 7. That is what is you have to do. So now as I told you, so it may happen that some of the prime implicants will be essential, so those have to be there, but other cases it may happen that say P1 is having actually say 1 and 3, okay, and then P2 maybe say having 7, no one else is having this one, and say P3 is having say 3 and 5, okay, and P4 is having say in this case say having 1 and 5. So this may be your picture say. Okay. So P1 is having 1 3, P2 is having 7, P3 is having 3 5 and P4 is having 1 5. Okay. So P2 is obviously have to include because it is covering 7, no one else is there. So obviously you have to include P2. Now you can see that if I take P3, then I cover 3 5 1 3 5 and 1. Okay, so 3 5 is covered, or I can do one thing also, I can also take P3 and P1, then I will also cover P1 3 and 5. So I can take either P1 P3 or P4, I mean you can take these two or you can take these two. So anyone you can take, but now which you have to take. So anyone you can take and your job will be done. That means what? You are taking the prime implicants in such a way so that this is covered, this is covered, this is covered and this is covered. So actually they are actually called a cover. Okay, so now how you can do it? So you have to select a subset of the prime so that all the mean terms are covered. So we will find out in this lecture that how we can do that. This is actually called Quinn-McCluskey procedure, which will be illustrated by example. This is actually called the Quinn-McCluskey procedure, in which case you select the subset of primes so that everything, all the mean terms are covered. So now now if you can find out there is a choice of P1, P3 and P3 and P4. So which pair you will take? So we will take those mean terms actually which are having less number of literals. So if one mean term actually prime implicant is having say X, Y, Z, A, B, and another mean term say some P1, say for example is having X, Y and some A prime or something like this dot dot dot. Okay, then obviously which one is having less number of mean terms, or sorry, less number of terms will be taken into consideration. Okay, so that is the basic idea, and it is also obvious also. Okay, so you have to take the minimum, it is a subset problem, that you have to find out the proper subset so that it covers all the terms. It is a subset covering problem, and again if you can look at any theoretical computer science book, you can find out that subset covering problem is also a NP complete problem, which is also very difficult to solve. There is no well known polynomial time algorithm to solve the problem. So again we go for some heuristics and all, so that we will see later, but overall the problem is a subset covering problem, because see what you have to do, you have to given some prime implicants has been given, you have to find out a proper subset which cover all the mean terms. So it is a subset sum problem. You can map it to a subset sum problem, which is a NP complete problem, and so you have to go for heuristics or the time taken will be very large. Okay, so let us see the subset type prime problem. So basic philosophy I think is clear to you. The basic philosophy is you have to cover all the mean terms and for that we have to take a subset of primes. So you have to essential primes will obviously go in, because essential primes have some mean term which is available in no other prime implicant, so they go in. Now after that you have to take a subset from the remaining primes such that all the mean terms are covered. So sometimes we will get a choice, as I have given in the last lecture. Last slide. So you get say we had said that P1 is 1 and 3, P3 is 3 5 and P4 is 1 and 5. So you can take either P1 P3 or P3 P4. So if you take any one of them, 1 3 and 5 will be covered. So how to go about it? Okay, so let us take this one. This is the sum, and if you go for a complete sum of the by iterative refinement, iterative consensus, you can find out that this will be the complete sum, that is sum of prime implicants. So these are your prime implicants. Now the condition that any subset must satisfy is that each mean term has to be included in at least one prime implicant, which is the subset. So now you have to we can say that P1, P2, P3 and say P4. Now you have to take a subset of this such that all the mean terms for which the function is 1 has to be included in either P1, P2, P3 and P4. That is very obvious, that is what is the requirement. Okay, so this actually a subset of prime implicant that satisfies this requirement is called the SOP cover of the function, or simply a cover. That is, if you take say P1, P2, then it says that it covers all the mean terms of this function, then you say that P1, P2 forms a cover. You find that P1, P2, P4 actually requires for that, so you will say that P1, P2, P4 is a cover. So there can be many other options also, like you can say that P4, P3, P2 can also be a cover. Now among all the choices, which one we will keep? We will keep those choice of prime implicants whose subset a subset of the prime implicants. If there are multiple choices available, which one you will take? We will take that choice where the prime implicants have a minimum number of literals in them. Okay, the concept of cover, now we will see that. Now it is actually, till now it was circuit, Boolean expression and all, but now we will see that while we are solving this computational problem, we do not require to think about circuits and all, it can be represented by a constraint matrix. So what is that? So each column of the constraint matrix corresponds to a prime implicant, and each which row corresponds to a mean term. That is, we will have a matrix like this. So this one will be your prime implicants P1, P2, P3 dot dot dot, and here will be your mean term 1, mean term 2, mean term 3 dot dot dot. So whatever the mean term will be there, that has to be here. So here one point I have to say that at this point again I am blowing up my function. So I mean, at least let me not blow it twice. So this selecting subset primes by the method I have told you is an exponential problem. Again we can see if there is some other way of doing it which can bring down the complexity, but it is a very difficult problem to solve as it is. So in the next lecture, so next to next lecture, in these 3 lectures we will only see about the exponential algorithm, and after that we will go for a heuristic. So in this lecture we will see that the problem is difficult to solve in a lower complexity because it is an incomplete problem. So what is our agenda now? Our agenda in these 3 lectures is that, so at least we have seen that we can, if you go for the tabular method to generate the prime implicants, you have to blow the function up. But if you go for iterative consensus, at least for generating the primes you are not blowing up your function. But to generate the subsets, so generate the subset of primes or going for the cover, you require to know which mean terms are covered by which prime implicant. So at least you have to again blow it up the function itself to find out the mean term. So that you have to do anyway. Okay, so at least we are not blowing up in the first phase. So see, now we are solving it in 2 phases. First we are generating the prime implicants, and then we are generating the subset of prime implicants which cover it. So if you now you can open up the function by blowing it up, that is if you represent a canonical method, then obviously all the mean terms are brought out. So if all the mean terms are brought out, then you are blowing the function. So we have tried to avoid it in the first step. We avoided it by going for iterative consensus. But in the second step, where you are generating the subset of primes, here you cannot do that. Here you have to open up the mean terms, and we actually have to see the cover. We see how we do the cover. So here actually the problem is again you have to blow it up. So at this stage again we have reached the exponential part, exponential complexity. But still this is a 2-part problem. So we are solving it in 2 parts. In the first part at least we have avoided it a bit. Okay. So we are representing it by a constraint matrix. So here all the prime terms are there, prime implicants are there, and 1, 2, 3, 4 are the mean terms. So here it can be order of 2 to the power n. Okay. If the expression is 1, and you can say that all the prime implicants, all the mean terms possible are there. So all terms like 0, 0, 0, 0, 0, 1 dot 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 to 1, 1, 1, 1, all are the mean terms. If you say, then this will be a very long and it will be exponential. And then we put a 1 over here if this prime implicant actually covers this mean term. This is what is the idea. Okay, Cj be the element of row I column j, Ci is 1 or 0 if the jth prime implicants cover the ith term. If this jth term, if we put a 1 over here if the jth column covers the ith prime implicant. That is how it is done. Let us see an example. So in this case x, y, z, and these were your prime implicants. Okay. So let us take the assumption in this case, and these are your mean terms. So this you have to blow it up. Nobody can help you there. Okay, it's a blown up function. So if it's a 3 variable function, so the order can be 2 to the power 3. This length, the number of rows in this case. Okay, and if it's an n variable function, so the number of this row size can be 2 to the order of 2 to the power n, which is exponential. So overall, the subset covering problem itself is an exponential problem. We start off with, so we have 2 to the power n here, and the number of prime implicants can also be in some order of k or something. Okay, that can also be exponential in the worst case. And again we find out, you have to solve the problem, right? Then you have to find out which of these prime implicants that I take will cover it. That will again exponentially 2 to the power n. So that is again exponential if you consider this to be capital N. So that problem is actually 2 to the power n. So in this case it becomes a doubly exponential in the number of variables. So it's a very difficult problem to solve. Okay, so like all other stuff like this what you can say the scheduling problem, etc., they were actually exponential in the number of steps or exponential in the number of operations and so forth. But in this case it is doubly exponential in the number of variables, or it is exponential in the number of terms. In this is the problem space. Okay, so these are your prime implicants and these are your mean terms. So this problem space is in the order of 2 to the power n, where n is the number of variables. And to solve the problem actually this is capital N. So to solve the problem is 2 to the power capital N. So in the other way it is 2 to the power 2 to the power n. So this is a very difficult problem, and in terms of time complexity. So in the next lecture, in the new fresh lecture, we will see a procedure called espresso, which actually is a heuristic which can give you the minimize Boolean function representation in a heuristic manner. Okay, so we will go about it in next lecture. Now we start off with this, how do you go about this cover problem. Okay, so in this case we have see these are the 3 prime implicants. This will let us write x y prime, this x prime z prime, this one is y prime z prime, and this is x y, sorry y z. This is yz. Okay, now you see why do you put a 1 over here? Because this one because x prime y prime z prime is x prime z prime. So, obviously, this guy is this mean term is included in prime implicant 2. Similarly, it is y prime z prime. So, y prime z prime. So, even this term is actually included in prime implicant number 3 and so forth, but this one is not implicated with yz. So, this is y prime z prime. So, this is not included over here. So, you can easily find out that. Similarly, I can draw out this matrix. So, wherever I have a 1, a 1 is over here means x prime y z prime is included in x prime y. That is a simple idea. The whole matrix has been drawn. Okay, now you can forget about the whole circuit business, whole minimization business. You can forget about this. Once we make this matrix, so this matrix is made and your job is done. So you can also write it as 1, 2, 3, 4, 5. Done. Now forget about VLSI, forget about circuit. Now it's a constraint matrix based problem. Now what you have to do? You have to find out which among a subset of P1, P2, P3, P4, Pi1, Pi2, Pi3, Pi4 rather, okay, to be formal. So, this prime implicant 1, prime implicant 2, a subset of this such that the whole stuff is covered. Whole stuff is covered means in this case if I take P12, that means it is covering term 1 and it is also covering term 2. Okay. Then if I take Pi4, then it is covering 3 and it is covering 4. 1 is remaining. So, if I again take this one, so in this case 5 is also covered, some of the terms will be covered twice, that is not a problem. So, you are taking Pi2, Pi3, Pi4, if I take this, then all the terms are covered. So, you have to take a subset, minimal subset of this one, so that all the prime implicants are covered. So, let us see how can it be done. Okay. So, now that is what I told you. So, selecting a subset of primes. So, a constraint matrix we need a subset of the columns, that is minimum cost columns which cover all the rows. Okay. In other words, every row there must be at least one column which is a 1 in this row. That is, I mean, for some of the columns you have selected, now the requirement is that for at least one column each of these rows should have a 1. Okay. That is what is the idea. Okay. So, now in the example, now we will actually go about this example. So, now how do you go about it? Sorry. So, in this case we have to first see that. Okay. So, let us first see in this case what they are saying. So, see that note columns Pi and this may be part of every solution. Now, why? Now, you see this the two columns very important. Okay. So, you see this is a row, this is a row. Okay. To cover this row 1, 2, 3, to cover this is called singleton row. So, 1, 2, 3, this is 4. This is 5. Okay, so, to cover this row you have to be very careful that there is only one column where is the 1. So, it is a singleton. That means what? Pi4 must be taken. If I do not take Pi4, then nobody can cover this row number 4, because there is only one in this case. Similarly, also for this term 5. So, there is only one in this row. This is called a singleton row. These 32 rows which are singleton. That means what? To cover this row, Pi3 also has to be there, because only one column which is there, and for also for this case. So, Pi3 and Pi4 becomes two essential primes, or they must be included, because Pi3 and Pi4 actually contains one term. In this case it may be this one, where it is not present in any other mean term. So, actually Pi3 contains a term corresponding to this one which is no other term. Similarly, Pi4 contains a term corresponding to 4 which is no other term. But again, now in between these two you can take any other. So, if you take this term, obviously this one is covered, and if you take this term, this one is also covered and this one is also covered. Okay, so, now remaining one is 2 and 3. So, if you take P1 obviously these two terms are covered. So, you can take if you are taking 4, obviously this one is also covered, this one is also covered. Now, the question remains about 2. So, 2 is left blank. So, to take 2 you can take either P1 and P2. So, let us again recap quickly what we have seen, we are discussing slowly. So, you see this is a singleton. So, you have to first find out the singleton elements. That means, to cover this one Pi3 has to be taken. So, if you take Pi2, this one is covered, and obviously this one is also covered because it also contains this one. But by virtue of this one you have to take P3. Now, this one also by this row is singleton. So, if you have to cover this element, you have to take Pi4, but it is obvious if you take this one is covered. Okay. So, now nothing else is covered, obviously this was also a 1, so it gets by default covered. By default, by this virtue of this we selected Pi4, which in turn covered this element also. Now, we have only one thing remaining, that is number 2, so which can be covered either by this or this. So, you can take either P1 or P2. So, these are the essential primes which you have taken. Now, P1 1 or P1 2, any one of them you can take. Now, it depends which one of them has more number of literals or which one has more number of stuff. So, in this case if you think, in this case is okay. So, Pi1 and Pi2. So, I think I will select this one because it has only one complement. So, it has two complements in this case. So, you think complement means a buffer. So, my choice will be this one. So, like it may also have, if sometimes this has more number of literals, more number of literals, you can avoid this one. So, this is a simple way of doing it. Okay. So, this pi and this one is a part of every solution because these some rows are singleton. Now, it must be noted that because of the prime implicants this one and this one, so this one which is not in many other implicants. So, this is actually a essential prime implicants. Okay. Now, what we have done? So, now if we have that is what is this is the reduced matrix. So, how it becomes a reduced matrix? Because by virtue of this one we take this is gone, and by virtue of this is finally we saw that finally this is the only thing that remained. So, again I mean just quickly again very quickly we do that. By virtue of this singleton this one is taken, this one is taken, this one is gone. By virtue of this one 4 is taken, this one is covered and this one is covered. Okay. So, now you see only this element remains. Okay. So, this element remains. So, this one they have taken it over here. Okay. So, this one is the case. So, anyone you can combine either P1 or P12. So, in this case it depends on number of literals in P1, number of literals and so forth. In our case I think we took this one because just one negation was less. So, this is what is been done as a covering problem. So, this is the way we do it. So, there will be a proper algorithm which will be maybe we will be taking in the next class, which will be taking about you to a very there is a algorithm which will I discussed that first you find out the singleton elements, then you keep on decreasing it, then finally land up to this one, then you select either this one and this one. So, in next class we will be looking at a very proper algorithm for this one. But then now let us try to see about how we can what are the preliminary steps or pre-processing steps for going to the algorithm. So, in this case this one is the idea. So, we can write it in terms of a formula also we can write that it is a py3 dot pi4 dot pi1 plus pi2. That means what? You have to take P3 and P4 and among P1 or P2 you have to take any one of them. This also you can represent in terms of an equation. Okay, this is why you can see it. Okay, now so now what we will be doing? So, now we will be looking at some preliminary steps or pre-processing steps before we go to the exact algorithm which will be doing what I have done now. So, we have started with this one, then we have removed the singleton elements, and then we have got to this matrix where there was a choice and then we can take any one of them, so forth. So, that was actually nothing but a way of there were some steps of solving the subset of prime covering problem. Okay, so now in the next class we will be going about a formal algorithm or a exhaustive algorithm, or I should not say exhaustive algorithm, a formalized steps for doing it. But before that we have to go for some pre-processing of the matrix, so that the matrix can be made smaller in size if it is possible. Okay, so we will try to make the matrix as small as possible. Like for example, if you have some singleton elements, singleton rows, so they have some single rows means some of the prime implicants has to be selected by default. So you select them, your matrix will become smaller, and some ways we will make our matrix smaller, and then finally with the remaining matrix we will apply the algorithm to find out the, if there is choices. Like in this case final matrix was this small where you have to take a choice. So similarly these are actually as you can think that removing of the singleton stuff like this was nothing but the singleton stuff and all those things were some pre-processing. So now we will see all the pre-processing cases, so that your matrix size will become smaller and smaller, and finally when you will have to run the choices among some choice sample space, you have to take a path or some paths, then we can have a smaller matrix in this case. Okay. So as I told you that once you have this matrix, then it does not remain anyway a VLSI problem, it becomes a computational problem as such. So I will take an arbitrary matrix and start. So you see this is an arbitrary matrix. So this is a very special kind of arbitrary matrix which is called a cycle. Okay, in this case you see there is no singleton row. That means there is no row which is having only a 1. See, this has 2, this has 2, this row has 2, this row has 2. That means in this case no prime implicant is an essential prime implicant, because there is no row with a single one. That means there is no row which is having a mean term which is available nowhere else. So in this case, what you have to do, say for example, there is a lot of choices over here. So it cannot, here you cannot directly reduce the matrix. So you see it is 1 1 1 1 1 1 and 1 1. So this is cycle. So this 2, then this 2, then this 2, then again it will be cycling. This is called a cyclic matrix, because in this case there is a lot of choices. So you can say that I will take P1. So if you take P1, so this term is covered and this term is covered. If you take P1, remaining are these two. Now you can take P3, then again this one will be covered and this will be covered. So P1 and P3 you can take. Similarly P2 and P4 also you can be considered. If you take P2, then this one will be gone and this one will be gone, and then if you take P4, this one will be gone and this one will be gone. So any two you can take. So you see here the matrix is not be able to reduce, but there are a lot of choices. Okay. So this arbitrary matrix, each row is covered by exactly 2 columns and each column is covered by exactly 2 rows. There is no essential primes. There is no apparent reason to prefer one column over the other. For this matrix we must proceed by choosing one column arbitrarily and find the best solution to the assumption that the column is selected. We must then assume that the column is not in the solution and find other space. This process is repeated, then the whole solution space is explored. So this one is a with the cyclic matrix where we have to take this way. So that is they are talking about in this in this paragraph we talked about the general procedure which will be highlighting in next class. So, in this is a special matrix where there is no reduction possible. So, what you do, you say take P1 and then if you take P1, so this is covered and this is covered. Now, you have now this remaining part is this one. Remaining part is so if you take the P1, so this is covered and this is covered. So, remaining is this one. To cover mean term 2 and 3, the choices are you take Pi3 both will be covered, or you take Pi3 you take, or you take P1, P2 and P4. So, the new solution space. So, what we do here, arbitrarily we take one row or sorry one column and then again repeat by doing the problem. So, here I think it is a small one. So, you will obviously take P3 because it will cover both the terms, otherwise you have to take 2 mean terms. So, I mean in the next class when we are taking a real example, a large example, the things will be more clear, but in the nutshell what I am saying you that in cyclic matrix there is no reduction possible. So, you arbitrarily take one column, okay, in this case I took this column and then again try to redo what I am doing. Then again you see this is the subset problem, this is a subset of the problem, then again you see that which is the best way to do it and keep on doing it. Okay. Okay, so what basically so in the previous examples we know 2 important mechanisms of doing it. So, what was that? Reducing the constant matrix which are singleton and then exploring the solution space in case of cyclic cones. That is the 2 ways of doing it. So, first we reduce the matrix as much as possible, and then if we land up to a cyclic matrix where no reduction is possible because there is no singleton over here, then what we do? We take one column arbitrarily and then again try to see which are the next best solution, and say also you can find out. So, here we find out that next is better solution is this one. So, now if we have taken another column this one, then solution space could have been different. So, now you can again drop this and then start with this one and then again see what is the cost. So, it is again a branch and bound kind of a problem. So, you take one solution and see what are the solutions available. Then you do not take that solution and take another path and see what is the solution, and then try to find out the minimum cost solution in this way. Okay, and this is a special case when it is cyclic, when there is no reduction possible. So, we will discuss algorithms to do these tasks in the next class, but before that we will covering problem of the constant matrix formally. Okay, so, we will next before that we will see the covering problem of the constant matrix formally, that almost we have discussed how the matrix would look like, but let us see it, and then see it can be the problem of minimum cost that cover all these rows can be thought of independently of Boolean functions, mean terms and this one. So, what it says that now we will see that this whole problem of subset of sign prime selection problem is independent of prime implicants, mean term functions, etc. It is nothing but it can be thought of minimum cost columns to cover all the rows. So, this is actually what we are going to do. That is we have a matrix, some rows are so if the column is having a 1, that means that column is covering some row, and then you have to find out the minimum cost or the minimum number of columns such that all the rows are covered. Okay, that is actually called this one, that is minimum cost columns that cover all the rows. So, this is the problem, and we can forget it independently of circuit, functions, mean terms, etc. Okay, so so now we will represent our problem in a formal way as we have said. So, in this case we have seen that we have to cover 4th row and 5th row. So, okay, that is Pi4 or this one is there, if you just look at it, not this one. So, this example if you check, so Pi3 and Pi4 had to be covered. So, you write this way. So, we write that Pi3 has to be taken and Pi4 you have to take for 4th row and 5th row. So, they were singleton rows, so you have to take them. Now, for the first row, for the second row and for the first row. So, first row can be covered by P1 or P3, just if you look at the matrix you will find out. Just look at it. So, first row can be covered by P2, P3, second row can be covered by P1 and P2, third row can be covered by P1 and P4. So, if you just look at it, so this is how your equation is. Okay. So, these are the singleton. So, P1 plus P3 first row, P1 plus P2 second row, P1 plus P3 for the first row, third row. Okay, so this is the equation for this is the equation terms of the matrix. Okay. So, now you can write this equation in this way. So, Pi and P4 are mandatory, then you can either take this 2 or this 2 or this 2, any one of them will cover the first, second and third terms. Okay. So, this one will cover the first term, this one will cover the second term, and this one will cover the third term. So, this one for first term, this one for second term, this one for third term, this fourth term and fifth term. So, single, so they are mandatory, and for 3 you can take either P1 or P4, P2 you can take P1 or P2, and this one for P1 and P3. So, any one of, so here one of them is to be true, here one of them has to be true, here one of them has to be true, and here it is by default Pi3 and Pi4 has to be true. So, this is how you can write the whole expression, whole constant matrix in terms of an equation, and then you have to find find out that which of them I will make as 1 should be the minimal cost one. So, more I can make P1, all of them I can make 1, but then all the for the columns will be covered, that is not my requirement. So, I have to make minimum this terms here 1, so that on the minimum terms having the minimum cost to be 1, still I should get the answer 1. So, it is a formal way of representing it. Okay. Okay, so I mean, so this is actually called the constant equation covering problem. So you can just read about this what I have told you, that is given in the subject. So here one thing is important, the cost of the, I mean, when we say about the cost, actually when we have to predefine the cost of each of these columns. So how do you define it? So as I told you, we are forgetting totally about the functions, about the Boolean circuits in when we are going for a constraint matrix problem. You can just give a cost, say 1, 2, 3, 4 based on the number of literals each of the prime implicants are available. Then you will select the subset, so that if there is a choice that you can take one column versus column 2, then we will take the one with the minimum cost. So cost will be written in terms of the number of literals that is in the mean terms corresponding to that column. This way you can do. So there is one important thing of the also is there, that none of the terms here are complemented. So this is like some kind of a Boolean expression itself. So x p1 this is some kind of it's a POS form, right? Product of sums. Some sums and it is a product, like the product of sums. So this sum, product of sum has to be 1 for some cases. So this is a POS formula also. Okay, but one interesting thing is that we do not have any epsilon, inversion over here, right? This is how we represent the constant matrix, and none of the term here you can see has a what you call complement over here. It is a POS, nothing. When we are representing the constant matrix in terms of PS formula, but there is no complement over here. So I mean, the idea here is that actually it is not by chance, it is what the way of formulation is something like that, because if we say that 0 here, that means we are not taking the column, and if you are writing 1, that means we are taking the column. Okay. We may note that all the variables in the constant equation are complemented. This is uncomplemented. This is not a coincidence, but rather a direct consequence the way the equation built. We do not put the concept not considering a column. Not considering a column means some value put at 0. The formula where no letter appear in both the phases is called a unate. Okay, so that means what? There is no concept of not taking. Not taking means not that we do not say that pi2 inversion means not taking it. You just put a 0 kind of a thing. It is not there. But obviously then you have to take a 1. Okay, so actually this is an equation where there is no complement. So that is actually it is also called a unate. A formula where no letters appear in both the phases. There is no complement. Or all complements. So that is also a non-unate, is a formula where it is a binate. Because of the form constant equation, we have the covering problem we are dealing with, sometimes called the unate covering. Because in our case we do not have any complemented terms in this POS formula, product of sum, everything is in terms of non-complementary version. So it is something called a unate covering problem. So that is why sometimes we call it subset covering, subset of primes. So some people also call it unate covering. So the reason is this one. This I mean does not have any much implication in the lecture on the procedure which we will be discussing, but why sometimes you may hear the name called unate covering in terms of subset of primes, then why they call it this way? So that is the reason, because the POS formula written, I mean that is actually representing your constant matrix, do not have any complemented terms, because complementation is no meaning here. We are not, I mean whenever we say that we do not require any row, we do not say that it is pi bar kind of a thing. If you do not take a row, you just put it as 0, that is it. Nothing else. So you do not require to represent any inverted stuff over here, right. So that is why it is also called an unate covering. So I mean sometimes we will be calling it unate covering, sometimes we will be calling it subset covering. So same way. So the unate covering problem can be defined in terms of both a constraint matrix and an equation. Like this is the equation and the matrix already we have seen. Okay. Then we will solve the unit covering problem of the constant matrix and we will be defining in the form. So in this lecture we will be only solve the UCP, that is unit covering problem in terms of constraint matrix, and we will define the problem in terms of matrix itself. Okay. So what is the matrix problem definition? You see, let M be a matrix of m rows and n columns, and Mij is 0 or 1 depending on whether the row covers the column. Okay, the unit covering problem finds a minimum cardinality column subset. So let this whole set of these columns is S prime, then you have to find a minimum subset S of that column for such that for all S, okay, there exists a m belonging to S prime, Mj is equal to 1 for all I 1 dot dot m implies that S is a subset of S prime. So what does that mean? In other words, the columns of set S cover M. Okay, so the columns of S you have to take, this is a subset actually. In other words, the columns in the set S cover M, cover the matrix in the sense that every row of M has a 1 in at least one of the columns in S, and there is no smaller subset S which also contains M. So what does that mean? You have to find a subset S, okay, such subset S of columns, okay, such that it covers M in the sense that every row of M has a entry 1 in at least one of the columns in S. So, you take some columns like this and it covers M, okay, such that means, so it has a 1 for this row, this one should have a 1 for this row, that is at least there will be 1 once for all the rows in the subset of columns S taken. And again there is no another subset S which is smaller than S and covers M, that means you have already covered the minimal one. So, in other words, what that complex mathematical equation states, it states that you have taken a subset of rows S, okay, and what does that S do? That subset S, what does it do? Subset S you have taken, okay, and then all the columns in S will cover at least once all the rows. Okay, that means there will be 1 in all the rows for all the for the columns covered in S, and along with that you cannot find another subset S prime which will also cover the matrix M and the size of S prime is less than S. That means S is the smallest subset possible. So, that is the very formal definition of this one. Okay. Now, we will, as I told you very quickly before we stop, we will see that how we can process the matrices before we go for the procedure of finding out the minimal subset or minimal subset of primes or the unit covering problem. So, what do you do? First, actually columns that have been singleton are mandatory, that is the pre-processing. So, given a matrix like this, all the columns by such column are deleted. So, columns that have a singleton rows are mandatory, like this is a singleton row. So, this is a singleton, okay, and this, for example, in the given matrix Pi is an essential column. So, now I have to find out, this is an arbitrary matrix. So, in this what we are finding, we are trying to find out all the rows which are having a singleton element. So, this is having a singleton element, that means Pi4 obviously has to be there. So, Pi4 you take, this one is being covered, you eliminate this, and by chance of this one there is also one in Pi4, because nobody guarantees that if there is a 1 over here there cannot be any other 1 in P4. So, in P4 there is 1. So, again mean term 3 is also covered. So, the matrix is now become smaller. This is the first way you have to do. So, first pre-processing is that you find out all the singleton elements, singleton rows, take the respective column and then make the matrix reduced. Okay. So, in this case Pi was an essential column, that means it is essential prime, and reduce the matrix accordingly. Okay. Now, so this is the simplified matrix. Okay, this is how we are making this. Next one is, next way of reducing it, if a row Ri of the matrix has all ones of another Rj, then Rj is covered whenever Ri is covered whenever Rj is covered. We say that Ri dominates Rj. So, let us see the matrix, then we will come to the definition. In the example below, mean term 1, so mean term 1 you see has all ones of another row mean term 2. So, you see this has 1 and 1, and mean term 2 you see this is the common part of it. So, this is the larger part of it. So, that means what it is saying? It is saying that if a row Ri of the matrix, so this Ri of the matrix has all ones. All ones means you see these are the 1 ones and these are also the 1 ones. So, it has, so row 1 in this case, that is Ri in this case, have all the ones for another row Rj, okay. That is because this has some extra ones that is allowed, but for row 2 you see it has all the ones in all the positions of ones in 1. In other words, what I am saying, for mean term 2, that is Rj in this definition, it has a 1 in all the positions where Ri has a 1. So, in this case these are the ones. So, Ri can have some more extra ones, that is not a problem, but Rj should have ones in all the positions where Ri has a 1. So, then we say that Ri dominates Rj. So, here mean term 1 dominates R2. That means what? Now, it is very interesting. So, now what we will do? So, Ri dominates Rj. Now, in this case what we can do is that simply we will remove the dominated row. Now, see interestingly what will happen, you just eliminate it. Now, what happens? So, if we are just eliminating the dominating row. So, dominating row you should remember that has more number of ones than the row being dominated. So, if you remove it, now somehow you have to select mean term 2, that is obvious. So, it can be either selected by Pi2 or Pi3. So, whenever you take Pi2, so mean term 2 will be covered as well as mean term 1 will be covered. If you take mean term 3, okay, then to cover this, then what will happen? So, if you take mean term 3 to cover row 2, so obviously this one will be covered, and by virtue this one mean term 1 also will be covered by this one. So, now so what happens? So, it is very interesting that if you remove the dominated row, then there is no harm, just remove the dominated row. So, if you dominated row, then the dominating row you remove, the row being dominated, that is row 2 will be there. So, if it will be there means it has ones in all the parts, in all the places the row dominating had. Okay, so, in this case you see these are the 2 places 1 will be there, and obviously by the definition these 2 must be 1. So, you have to cover mean term 2. So, either we will take 2 mean term 2 or mean term 2. So, by automatically mean term 1 will be covered. So, that is actually called elimination of the matrix or minimization of the matrix by row dominance. So, it is very important, but interestingly the row dominating row will be removed, the row being dominated will remain. So, if I think that this is the dominating row and this is the row being dominated, this is being dominated and this is the dominating row. So, if I do the reverse, so if I remove this row, the row being dominated, if I remove, then there is a problem. So, mean term 1 can be selected by this one or this one or this one, it is covered by this one, this one, this one. So, if I use P1 or P3, then automatically P1 will be, mean term 1 will be covered and mean term 2 will be covered. But if by chance I do not select these two, then I select P1, then only mean term 1 will be covered and mean term 2 will not be covered. So, that is why if I keep the row that is dominating, I may be in a problem. But if I keep the row that is being dominated, then I will not be in a problem, then I will remove this, I will keep mean term 2. So, obviously this can be covered only by Pi2 or Pi3. So, what will happen? So, if I cover by Pi2, automatically 1 will be covered, and if I cover by Pi3, automatically again 1 will be covered. So, yeah, that means if I keep the row that is being dominated, automatically the row dominating will be, the dominating row will be covered. So, in this case if I keep mean term 2, automatically mean term will be covered. So, that is the interesting thing. So, we first find out the row which dominates and then we remove the dominating row. Okay, and the row being dominated will remain. So, in this case this is the example, then again we can make the matrix smaller. So, in this case you see so in this case you see they have eliminated 1 and finally the matrix actually is this one. So, the reason as I told you that is given over here, that why we remove the row dominating row and keep the row being dominated. Okay. So, now yeah, so this is now we will see about the row by column dominance. Okay. So, I mean this is the definition. So, we will come back to the definition after the example. So, again in this case if you see, so this we can see that here if you now will be column wise. Okay. So, in the column wise if you see, so this row number 2 is having 1 in all the places, row 1 has a 1. Row number 3 is having a 1 in all the positions, Pi2 has 1s and Pi1 has 1. So, Pi2 dominate P1, that is obvious, and Pi3 will dominate both Pi1 and Pi2. So, in this case Pi2 will dominate Pi1 because it has a 1 in this position and it has extra 1. Pi3 is actually dominating both Pi1 and Pi2 because it has 1 in the positions and also in this one, and this has the extra 1. So, Pi3 is the dominating row for both Pi1 and Pi2. Now, what you have to do in this case, how can you make the matrix smaller? Here actually it will be just the reverse way we have done in for row dominance. In row dominance what we have done? In row dominance we have removed the dominating row. In this case we will do the reverse. We will actually keep the row which is dominating. So, in this case we will keep the dominating row. Now, because if we take Pi3, so obviously this one will be covered, this one will be covered and this one will be covered. So, obviously we can eliminate this row being dominated, sorry, columns being dominated. So, just you have to understand there is a slight philosophical difference. In the case of row dominance, we eliminate the row that is dominating, and in case of column dominance, we eliminate the rows that are being dominated, just the reverse. In column, we keep the row, if you keep the column which is dominating, because our column is better which is having more number of ones. Why? It is better because more the number of ones in this column, more number of mean terms will be covered. So, that way you can remember. So, that is why I will keep this and I can eliminate this. So, this will be your reduced matrix. Okay, so now what is the philosophy? The philosophy here is if a row has more number of ones, that means more number of mean terms it will cover. So, you keep it. So, now this row is dominating this one, means this column is dominating this column, means this column has more number of ones in this one and all in the similar positions. So, obviously if I take Pi3, so it will be default covering this, this and this. So, there is no more requirement of Pi2 because this is a common point here. That means Pi3 has more number of what you can say that Pi3 has more number of mean terms which is covered by P3 than Pi2, and this is a subset. So, if you take this, obviously there is no more requirement of this one because automatically it can cover up the case. So, your matrix will become reduced. So, the philosophy is this one, and in case of row dominance, see the definitions are same, but in this case we keep the one with a lesser number of ones and we eliminate the row with having a more number of ones, because if we keep the row with a more number of ones, then there is a probability that you select this column to cover and then this row 2 may not be covered. But if you keep the row which is having the less number of ones, then you have to, if you are just keeping this row number 2 is kept, then you have to cover by P3 and or P2 or P3, any one of them. So, automatically default row 1 will be covered, but if you keep row 1, then you will be maybe in a problem because row 1 may be covered by Pi1 which is not covering 2. So, in other words, this row dominance and column dominance definition is same, but in case of row dominance you keep the row which is dominated that is you have less number of ones, and in case of column dominance you do the other, you keep the column which has more number of ones, that is dominating, because in column we require more number of ones, because the column having more number of ones means more capability of covering the rows in a single prime implicant. So, that is the idea. Okay. So, with this we come to the end of this lecture. In the next lecture where we go, so these are the 3 preliminary steps we have seen. The first step is remove by finding out singleton rows, then go for row dominance, column dominance, and make the matrix as small as possible. After that, if it may become a cyclic matrix or some other matrix where no more reduction can be possible by row dominance, column dominance or singleton, then you have to go for iterative or a branch and bound technique to find out which is a good solution or the minimum solution of subset covering problem or the unit covering problem. So, that we will see in the next lecture. Thank you.